All right, so we'll get started for the next presentation. All right, let's get started. Okay. Hi, everyone. So my name is James So. I'm a faculty here. And I'm really excited to kick off the presentation of our Hoffman E project with several great colleagues here around data for generative AI. So it's often been said that data is the fuel for AI, but I think especially for generative AI, this is particularly true, right? So a lot of the recent advances that we see in generative AI, like language models and diffusion models, are really driven by new models that just soak up tremendous amount of data, right? Tremendous amount of human-generated data in particular. And this plot here is one visualization of this, where if you look at like the top blue curve in the plot, that's sort of an estimate of the totality of the human-generated text data that's publicly available. And then the second blue curve that's rapidly increasing is our estimate of how much data is already being used to train the different language models. Right? You can already see that the current large language models have been trained on a substantial fraction of all human-generated data, and so are estimated that within the next 2 years, that the model will have seen all of our data. Right? And now it's increasingly being trained on synthetic data that are generated by AI themselves. And I think this has many tremendous implications, both opportunities and also challenges. Right? And we're already seeing some of the challenges. So for example, just a couple of weeks ago, there's this really landmark settlement from Anthropic, where Anthropic agreed to pay basically the largest copyright settlement in the US history. They already paid $1.5 billion to authors to compensate these authors for using their books to train the Anthropic language models. In parallel, there are also ongoing similar discussions and lawsuits for OpenAI and other companies with other data providers. Right? And I think this really illustrates that if we want to build the next generation of responsible and effective generative AI models, we need to build a very strong foundation of thinking about the role of the data in these different models. And that sort of motivates the core topic for our Hoffman E project, which is really centered around this driving question around how does really data shape generative AI, and how can generative AI models reshape the data that we see all around us? And we organized our project around two related and complementary questions. So in the first question, we want to look at the data that's created by AI. Right? So this means looking at what is the AI-generated data, how is that being used all around us, and how can these kind of synthetic data shape and potentially benefit society if they're used responsibly. And the second question we looked at is looking at the data that's used by AI. So this involves looking at the training data that goes into these different models, thinking about how can we improve the efficiency and composition of these kind of data, and also understand how does the training data affect the creativity and the behavior and biases of these downstream models. So we're excited that in the presentation today that we'll touch upon both questions. Right? So we'll present 5 related research projects that speaks to both questions. So in the first half, we'll focus on thinking about the data that's created by AI, right? The synthetic data. So we'll talk about first give a survey of how do we quantify how much synthetic data is already available around us. And then my colleagues will present how these kind of AI-generated synthetic data can be used for public impact and also for training AI models themselves. In the second half, we'll talk about data that's actually used by AI, right? So this will think about data attributions, understanding how different kinds of training data affects the model behaviors. In particular, thinking about the sources of creativity and capabilities of these different models that come from both their training data for both diffusion models and also for large language models. So I'll just start by giving a brief survey to quantify the amount of kind of AI or language model generated data that's already all around different aspects of society. So we became interested in this a couple of years ago, where myself, like many people here, when we're reading research papers, we start to notice that certain specific words starts to pop up more and more frequently in these research papers. Right, so we did like a quantification of this, where you see that words like commendable, suddenly around 2023, you see a large spike in their usage patterns in scientific papers, and similarly for these other words. Now, many of you might have guessed that the commonality among these different words I show here is that these are words that are much more likely to be used by our large language model when they're writing research papers than they're to be used by human writers, human researchers. So basically, there are these kind of differential usage frequencies between words more likely to be used by AI versus by human. And we can actually leverage that differential word frequency usage to build a statistical model to quantify how much of a text that you see around us is actually written by language models versus by humans, which is what we did. But then we applied this statistical model to different kinds of corpus of text. So here we applied it to actually different scientific research papers that you see on the archive. So the y-axis quantifies the fraction of the text in these papers that we can estimate by our model to be written by LLMs. So for example, if you look at papers that are under the computer science section of the archive, so close to 20% of the text in those papers now are written by language models, and similarly for the other disciplines. Beyond research papers, we can also apply similar methodology that we developed to other domains of society. Right, so here we're actually looking at all these consumer complaints. Right, so if you file a complaint, then your data might be a part of this. Right, so we can estimate that in the US, about 15% of the consumer complaints now are written by large language models. So this is actually looking at press releases from different companies, right? Here across the board, we see around 17 to 20%, or sometimes higher, of these press releases from different corporations are also now written by large language models. And now we're also looking at millions of job postings that people post on LinkedIn, right? So from those, we estimate around 10% of these job postings are written by LLMs. And now if you actually even look at international organizations like the UN, so around 14% of the texts and documents written by UN we think are actually substantially written by language models, right? And we can also look within the US, right? So here basically we're showing that across different states, what fraction of these consumer complaints are actually written by language models. You can see that it's actually quite consistent, right? So across all the states, usually between 10 to 20% are written by LLMs. They see a higher usage patterns in more urban areas. And what this really illustrates is that language model generated text, these kind of synthetic data, is already all around us. It's already very much influencing different aspects of society and the text that we read and also some of the behaviors and decisions made by humans. So next, my colleague and collaborator Dan Ho will tell us more about these kind of synthetic data from language models and how they can be used for public impact.
Thanks so much, James. It's such a delight to be able to share this work with you all. In 2020, Stanford High issued and organized a call for the National AI Research Resource, along with 22 other universities, to really invest in a kind of public compute and data infrastructure to transform the kind of future of AI. Here at High, we then convened a policy practicum that involved over a dozen students, researchers, and faculty, really to try to write a blueprint for how something like this could be brought to fruition. And what we realized very early on in that project is that while everyone thought the infrastructure part might be the hard part, we quickly realized that actually the hardware is going to be much easier, and the hard part actually turns out to be the theory of impact around access to high-value data that government agencies have that is not generally available. Think here of VA healthcare data, atmospheric data by NOAA. What we wrote in that report is that the Privacy Act of 1974 fundamentally challenges the notion of the National Research Cloud as a one-stop shop for federal data. And so here, what we really wanted to prototype was a way to solve that bottleneck of how to actually think about that data access component. We partnered with some fantastic colleagues here at the Center for Population Health Sciences, which has a kind of data lake of HIPAA-compliant, rich kind of healthcare claims, Medicaid, Medicare, insurance data. And what often happens in these kinds of secure data environments that have highly sensitive data, like the American Family Cohort data, which has some 40 million clinical notes on 1 million patients, is that you have to do a lot to actually apply for access to this kind of data. And so historically, government agencies have approached this by a really onerous onboarding process. I still remember having to track down multiple previously issued passports to be able to report all foreign travel to become a census-sworn researcher. And that's been kind of one model. The other model, of course, on the more technical side, has been to have a kind of privacy budget with differential privacy and other related techniques. And here, the kind of idea is really, can we combine the best of both worlds by having synthetic data that is made available to a broader group of researchers along with tiered access so that, for instance, colleagues could prototype on the synthetic data, get an understanding of whether this kind of research thread is going to be valuable, and then push over the code to actually evaluate on the actual data set, and then you can control the outputs via a typical kind of query budgets. We did a proof of concept using synthetic type 2 diabetes patient notes, where we built a kind of pipeline to build on some of the fantastic tools here by the Stanford NLP group to do de-identification and build an on-prem differential privacy protecting language model to generate synthetic notes. And then we turned to the domain experts really to understand how valuable is this going to be given the bottleneck of access to high-value data. And the responses by a small, albeit small, group of experts was fairly positive. 83% said they would not be able to distinguish real versus synthetic data. The vast majority would be willing to use it for grant proposals, but would still like to validate on real data, but noted that this is extraordinarily similar to actual physician notes. And it's a really exciting way to potentially broaden the net and expand researcher access to be able to unlock insights to this kind of data. There's a bunch of really interesting future directions here, for instance, around multimodal data that can preserve dependencies across tabular and textual modes. The plan is to have a full kind of A/B test to actually understand how much does this unlock a greater researcher access. And ultimately, the vision here really is to build out prototypes like this so that we can get something like the data component for the National AI Research Resource right. And with that, I'll turn it over to my colleague, Tatsu.
Thank you very much. And so now I want to talk a little bit about the basic science of synthetic data. In many ways, I think synthetic data has been billed as part of the component for the future of language models in AI. You just saw Dan talk about sort of synthetic data for public impact. And earlier, James was talking about how model-generated text, so in some sense, synthetic data, is sort of pervading the ecosystem that's the internet. And if you talk to people from many of these labs that are building these systems, you will often hear that synthetic data is a major part of overcoming these challenges in data efficiency. That somehow, by being able to have these models generate new kinds of data, that they will be able to, in some sense, learn something new. And so it is clear that synthetic data as this object lies at the nexus of many different important questions. But at the same time, I think discussions about synthetic data have been deeply muddled, right? Industry folks treat it, or often speak of it, as if it's this mythical thing that can solve all of our problems and break, the data processing inequality. Whereas, others who are more critical might say synthetic data is nothing but something that will cause models to just degenerate into bad behaviors. So really, I'm coming at this from the perspective of a machine learning person and asking the question of what is really synthetic data? Are there sort of serious mathematical and empirical underpinnings to bring clarity into this discussion about synthetic data and how we might use it reliably in cases like that public impact example that we just talked about? But really, one of the big challenges that I think once you start working with synthetic data that you realize is that unlike many other things that you might be able to study in the lab, like for example, small-scale architecture research for neural networks, or even language model pre-training, which you might think of as this thing that requires tons and tons of compute, synthetic data is uniquely challenging in some ways because it is very, very difficult to scale down. You need a model that is capable of generating fluent English and doing rephrasing and all of these manipulations on data. And so traditionally, synthetic data has really been the domain of industry researchers. One of the things that we've done as part of the Hoffman E over the last year is to come up with new ways, new sort of microscopes and experiment platforms for rigorously developing and evaluating synthetic data for model training. And one way of thinking about this is to say, the whole big pipeline problem of having a model improve itself, for example, is too difficult for us to tackle. But could we tackle a much simpler problem? For example, having a model generate synthetic data about a single textbook and having that go back into the model. That seems like a much more tractable problem. And this framework, which is known as continued pre-training, turns out to be a very fruitful one, as we've discovered over the past year. And using this platform, using sort of purely academic resources in collaboration with some folks, Emmanuel Candes in the stats department, we've come up with sort of new ways of generating diverse synthetic data to teach models sort of new facts. And one way, sort of the one kernel of things that demystifies synthetic data here is that we're not really creating any new facts per se from the data. What we're doing is we're using models to say rephrase the data or come up with different views on the same kind of data and putting that back into the model, in some sense making implicit facts explicit. So in this example, an algorithm we came up with called Entograph, we're looking at different entities that appear in a document, and we're asking a language model to come up with sort of relations between the entities that appear in the document. In some cases, making implicit relations between entities explicit training data for the model. And what you see on the right here is that if we generate these kinds of synthetic data, we can teach the model sort of new facts that come from really, really narrow corpora, which is very useful if you're trying to build things like domain-specific language models. But also, one thing that's really important and interesting about this is that now these same platforms, this sort of microscope that I spoke of, allows us to come up with new algorithms which we can then scale up at the pre-training scale. And so one of our most recent works along these lines is we collaborated with researchers from Apple to build a sort of pre-trained language model at the 3 billion parameter, 1 trillion token scale that actually uses sort of this synthetic data that's built from scratch. So in this case, we train a model once. That model is used to generate synthetic data over pre-training corpora. The model is trained on that synthetic data set, and the performance improves from the second pass. And so we're able to actually extract more information than we can with standard training practices using these processes. And we can validate this at scale using this strategy. Finally, I think one thing that's important for me to sort of communicate as part of this process is just how sort of empirically complex this phenomenon of data in general and also synthetic data is. And I'll leave you with one really sort of intriguing empirical phenomenon that we found over the past year. You might think that a really naive form of synthetic data, which is to generate straight from the model and then just to train on those outputs, would be something that is deeply, deeply degenerate. That you would have to do something like processing or filtering in order to be able to get performance improvements from a model. It turns out that's not the case. If you tune various specifics of this implementation right, merely training a model once, generating data from it, and then combining that with real data can actually lead to performance improvements. In some sense, you can extract more information simply from training on your own outputs, which is a really surprising sort of discovery that we've had over the last year. And it relates very closely to a lot of the wider societal discourse on sort of the impact of having model-generated content on the web and whether that might affect sort of future training rounds. So with this in mind, we're saying that this sort of area of synthetic data and a deeper understanding of data is a really foundational topic that we think has really deep connection to many areas of machine learning and even more broadly to areas like creativity. So I want to hand it off to Surya next to talk about his work on data attribution and creativity.
Okay, great. So yeah, if we're going to be using AI to generate synthetic data, we'd like to have a much deeper understanding of how it actually generates new data and how it composes its training set into new data set points, right? So for example, if you consider diffusion models, they seem to create endless amounts of creativity. Where is this creativity coming from? And can it be exponential in the size of the image, for example? So just to get everyone on the same page, the idea behind a diffusion model was you destroy structure and data through a diffusion process. And actually, the first diffusion model was invented in my lab where we were trying to think about how to circumvent the second law of thermodynamics and create order from noise. So we trained a neural network to reverse that process and go from noise to a structured image. It turns out it's possible to analytically write down a differential equation that does this exactly, but such a differential equation would only go from noise to one of the training set images. It couldn't be creative, right? So if the neural network were highly expressive, it could never be creative. So the creativity of diffusion models lies in their very failure to achieve what they're trained to do, i.e. to reverse diffusion. So if they fail, how can they fail in sensible ways that give you creativity? So we recently developed a theory of that. The basic idea is these diffusion models are not infinitely expressive. They have this U-Net architecture that has two key inductive biases. One is locality. That is, where each local patch of the image flows only depends on its neighborhood. And one is equivariance, is this rule that each local patch follows is invariant to where it is in the image, right? So then we can analytically write down the optimal reverse diffusion process subject to locality and equivariance constraints. This yields an interpretable differential equation that doesn't require any training And it provably leads to exponentially many new creative images that are patch mosaics of the original training data. So to explain, so you can sort of view the reverse process on the upper right as each local patch is flowing backwards in time and becoming a lot like one training set image local patch from some training set image. Another part of the image is flowing back and becoming another training set image patch from another point in the image. And then you get this patch mosaic. Okay? How well does this theory work? It works incredibly well. You're seeing across 4 data sets and 2 architectures, you're seeing pairs of images. The right-hand side of each pair is a noise fed into a trained diffusion model. And the left-hand side of the image is the same noise fed into our analytic theory. And you get a very beautiful match between theory and experiment that's about 0.9 R squared between theory and experiment in pixel space. We're unaware of any theory that's so highly predictive on a realistic architecture and a realistic data set. Again, our theory is analytic. It doesn't require any training. And that now we can attribute each local patch of a new image to which training set patch it came from, essentially. It also explains a funny thing about diffusion models, which is these hallucinations that they have. You all remember those weird 6 fingers and so forth. Our theory actually also reproduces these hallucinations. Our theories on the left, our experiments are on the right. You see, for example, pants with 3 legs, shoes with 2 toe regions. The reason this happens is because of excessive locality in the process. When, say, a part of the region is deciding to become a pant, it doesn't know what other parts of the image are, how many other parts are deciding to become pant legs. So that's why. So there's a duality between creativity and hallucination. So there's lots more to do here in terms of understanding more complex architectures and more data sets, but we're starting to get a handle on where does exponential creativity arise from in the synthetic data generated by AI, and how do we attribute new creativity to the original data set points. And now Sun will talk about data attribution for language models.
Yeah, so as we saw throughout this presentation, modern generative models are really driven by the training data they're trained on, and all its various form, whether it's natural or synthetic. And while this process might be too challenging to understand in general, we might try answering a simpler question, which is what's the marginal value of data? And so we can think back to the court case that James mentioned in the beginning, which was this court case brought against Anthropic by a group of authors recently. And sort of in this context, we might want to understand what is the counterfactual value of some collection of books that this model is trained on. Now, how should we define this? Let's make this more concrete by fixing some evaluation metric that captures the model capabilities we want to measure. And given this definition, a very natural way to define what the marginal value is to look at the difference between the value of the model trained on everything, including that data source, and versus the model trained without that data source that you're trying to understand the value of. And while this is a very natural definition to work with, sort of the main challenge of data attribution is that for any new data source you want to understand, you have to basically repeat this entire process. So maybe next you want to understand the value of New York Times, and basically that requires you to retrain a model from scratch on a new data set excluding New York Times. And this is obviously a very expensive process. And so really the field of training data attribution has focused on this challenge of sort of understanding when and how we can actually efficiently approximate these counterfactuals for all these different data sources that these models are trained on without having to actually retrain a bunch of times. And so fortunately, we've made a lot of progress on this problem over the past few years. And to give you a sense of sort of the kind of things we're starting to be able to do, here's an experiment that we did. And so here what we did was we pre-trained a GPT model from scratch on a bunch of internet data. And we looked at a bunch of different data interventions. So each of these points on the plot is a very small data intervention that's less than a fraction of the data set. And we look at 2 different quantities. So on the x-axis, we look at the ground truth contribution of that data source as measured according to the definition we defined in the previous slide. And then on the y-axis, we try to predict this ground truth value. And the crucial thing about our prediction is that all these predictions on the y-axis are predicted using a single training run of the model. So it's actually very efficient. And you can see that remarkably, we're actually able to make these quantitative predictions about these small marginal values of different data sources. And sort of the nice thing about these approaches is that it's sort of very general. So maybe you're in a different setting where you're already given a pre-trained model, and you're fine-tuning this model on some new data sources, and you want to understand which of these data sources are most helpful or most harmful. And you can see that the same methods sort of give you a way to pretty accurately predict the relative rank of how valuable different data sources are. So sort of zooming out, why do we care about data attribution? This data attribution gives this very principal way to assign data values to different data sources. And sort of there's really two different sides to this. On one hand, you might be the one building the model, and you want to understand what's the relative contribution from all these different data sources. But on the flip side, you might be one of the creators of the data. So maybe you're an author, maybe you're an artist, and you want to have a better understanding of how valuable the data was. And we are hopeful that some of these tools that we're developing sort of are building blocks towards building a functioning data market that involves both of these parties. And zooming out even further, we believe that data attribution really gives this sort of very principled quantitative way to probe how models generalize from data. And we saw a very nice example of that from Surya in the previous part. With that, I'll hand it back to James for the final part.
Great, thank you very much, Sam. So these different projects, I think, come together to form, I think, a really exciting foundational set of tools and frameworks for us to think about data in this era of generative AI, right? And as we saw, we've seen how we can study how much AI-generated data is already permeating the society all around us in terms of these LLM-generated text. And in the presentation from Dan and from Tatsu, we see how we can study sort of the foundations of synthetic data and also look at really high-impact applications of synthetic data towards healthcare and also broader societal problems. And on the other hand, right, from presentations from Surya, from Sam, we also see how we can build a really strong foundation to understand how the different kinds of data, both real and synthetic, affect the model behaviors, biases, and performance, and how we can use ideas like data attribution to understand also the creativity of these generative AI models. So I think together they form a really exciting and complementary perspective. So for next steps, one of the things that Stan mentioned is that we want to sort of deploy our synthetic data techniques together in collaboration with population health sciences here at Stanford to do a more a real-world deployment and randomized study. We're also scaling up the methodologies for this data attribution for larger language models and diffusion models. And also, as the next step, we're very excited about thinking about more of a mechanism design to think about markets of data for generative AI, right? Putting these different pieces of data attribution and synthetic data together to think about how do we really quantify the value of different kinds of data assets. And that also leads into sort of this broader analysis of the legal, policy, and economic perspectives of data, which we'll continue to explore next. So I want to conclude by very much thank Hoffman E and HAI for the generous support for our project. So it's been really fantastic collaborating with many folks across different aspects of these different projects across Stanford campus. And the team has also been very productive, and these are some of the research papers that's already published that are supported directly by the Hoffman E grant. So I'll just conclude here, and I'm happy to take any questions together with my colleagues.
Thank you. We'll invite the project team to take a seat in the front, and we'll open up questions to the selection committee first.
Thank you for the very interesting presentation. You mentioned legal and policy implications. What will be the first steps, or what steps have you taken?
So we have already done some analysis. So with looking at the copyright aspects of the synthetic data. Actually, do you want to say more about that?
Yeah, along with Mark Lemley, who's on our team, I've previously worked with him on, and Percy Liang as well, on copyright implications and fair use and the related implications of what happens when there's not a data market, what are legally viable and economically viable and computationally viable mechanisms for sort of resolving this space. And so we've been in discussions about those kinds of questions, and we're hoping to sort of think about, what is something that goes beyond sort of like licensing? Because licensing is a valid mechanism, but I think there's an information asymmetry between the labs and sort of the authors and others. And so coming up with technical mechanisms that will assist sort of, what are reasonable policies and also legally viable options, I think is, a really interesting question at the intersection there.
Just maybe to build on that, to connect it to some of the synthetic data for public impact stuff. I mean, part of the reason why we have this particular ecosystem where so much of the impetus of where work is being done is on private, oftentimes ad data, actually is a function of our legal system. It's in the wake of Watergate that the Privacy Act of 1974 is enacted, and legislators at that point in time were actually worried about systems of surveillance generally, but just went after government agencies. And so it turns out that actually that creates the structural difficulty of that the NAIR is in a sense trying to solve, of actually getting. So I think actually once we begin to understand the techniques that can be used to actually in a secure and privacy-protecting way gain access to that data, and it also lends itself to real questions around what does reform of something like the Privacy Act of 1974 look like.
Thank you. So we have a real world, which gives us data, and then we have a simulator, which gives us data, and we can build models from each. And I'm curious what you think about this idea of what's the approach in the sim to real analysis generally that would keep us aware of potential beat frequencies and moires and interference patterns that we just can't see with simple probes.
I can start off.
Hidden differences that would lead to gaps in how these models work in specific contexts that have not been probed.
Do you want to start? Okay, yeah. I think that's a really important question. And I think the current generation of synthetic data approaches don't really have a way of resolving those issues. Because the way that one might think about synthetic data now is that we take a big language model, we prompt it to do X and Y, and the output looks vaguely English, so that's good, right? And that goes back into the model. I'm drawing a caricature, but really, the reality is not too much more sophisticated. And so part of the thing that we're excited to do as part of this program is to come up with sort of more statistically grounded ways. So one of the things I was talking about, which I glossed over about the scaling up, that's actually doing it without prompting. It's all done kind of in a nice end-to-end way where we're using like neighboring pairs of documents as supervision to try to come up with ways of generating synthetic data. And we're thinking that if we can come up with good sort of statistically grounded approaches, then we can also maybe eventually get guarantees on the fidelity of the synthetic data that we generate.
One related question, which bothers me quite a bit, and it should be bothering all of us, I think, is going beyond the great first steps you showed with the value of data for specific tasks like ranking, for example, and so on, to going all the way back to the source of the creativity, let's say for scientific work, where the great intellects and their thinking is muddled into the several billion parameters, and no one knows where that came from. Even if it's a composition of A and B, where A and B were fabulous human contributors, we'll never know that. What's the prospect for, I mean, I know this is a very hard problem. What's the prospect for one day having the ability of these models to give us some sense of attribution, human attribution, in intellectual work?
I think in the, I'll talk loud. I think in the case, one case where we know really how to attribute stuff like, say, in images, we're actually looking at other things like protein folds and things like that. Because protein folding models or diffusion models for proteins are notoriously not very creative. They have too many alpha helices and beta sheets and all that, and we're trying to attribute the original folds in the protein data bank to what they create. I think for mass diffusion models, we can also take our methods and apply it in that setting. So when it comes up with a new piece of knowledge, we can figure out which parts of the training set led to that piece of knowledge. And then we could actually try to guide it away from that, right? You could try to have some kind of entropy regularization that guides it away from certain data points as it becomes too close to them, right? And try to get even more creativity out of it. But these are just research ideas at the moment.
On that note, it seems that one could try to be very different from whatever is out there, but it's very easy to create nonsense. And there's a boundary between what's creative versus what's good. I mean, it seems like two things are related but not quite aligned. And I wonder how do we deal with it? And then as far as creativity goes, it seems that some of the creativity that we see from generative AI today is a little bit like composition of known patterns, new composition of known patterns, versus every now and then remarkable human beings come up with something completely out there that nobody ever thought about. And that seems like in a different level, but I don't know like how to theoretically or in a principled way to differentiate the two types of creativity. I sometimes like to call that as interpolation versus extrapolation in a very hand-wavy way, and some people say, oh, that makes a lot of sense, and some people say it doesn't make any sense. I don't know if you have any thoughts on that.
I can actually say something. I also worry about the same question. I think it's a great question. I would say that interpolation in some very sophisticated latent space can look like extrapolation in some visible space. Like my North Star example is Einstein, where he did the thought experiment of somebody accelerating in an elevator in outer space, realized that they would feel like exactly how they are on Earth, and so therefore gravity is the curvature of space-time and so forth, right? I mean, we might be able to get there someday, but he had the right latent space and the right analogy to come up with. He came up with the initial thought experiment, and then everything actually follows logically from there, right? So I don't know how we can do that, but it's a great question. Yeah.
It's such a good question. If I could offer one perspective on it, our team's thought a lot about what does it mean to have creativity in legal argumentation, right? And there, one of the pathologies of if you just take something off the shelf, it'll come up with really creative but flatly unconstitutional or illegal arguments in all sorts of ways, right? And so part of what you then try to think about to really constrain this is, can you build out constraint identification so that you can explore the argument space in a way that still adheres to constitutional or statutory boundaries, but might actually push arguments in ways that litigants themselves have not discovered? I think that's some of the really interesting kind of ongoing work here to kind of navigate that boundary between creativity or things that are just plain wrong.
I want to go back to a really basic question that came out of some of your earlier slides, James. We see all this data, and we see a lot of the synthetic data, and that paper on model collapse a year or two ago, made a lot of waves in the community. What's the thought? Like, is this an issue we're running into, and therefore we need to really understand it, or do we now think, oh no, it's not a problem? Like, I didn't really see it directly addressed by what you're talking about.
Could I take that? Yeah. Kind of a sort of funny model collapse story is, one of my students and I wrote one of the first, or maybe the first model collapse paper back in 2022. And I think our conclusions were quite different, which is that really model collapse, or really we call it data feedback loops, isn't a thing that sort of runs away out of control. It's very contingent on actually the dynamics that surround it. So if you have a lot of real data coming in and also model generated data also coming in, then it's actually sort of stable and depends on sort of the proportion of the two. And maybe even more importantly, you can kind of think of the model training on itself as a kind of regularization of a form, right? In some ways, like when we dream and we keep thinking about our ideas, we're training on our own thoughts. And that sort of pushes us in certain directions, but it's not necessarily bad if the external conditions to stabilize things are right. And what I was talking about in one of the slides where I was saying, if you train on your own outputs, that can actually be good. I think the empirical phenomena here are extremely nuanced. And a lot of the discussions that we've been having about model collapse and even synthetic data, I think are far too simplistic because it really doesn't acknowledge the fact that it's all very contingent on the precise experimental settings and the environments in which we run these things. And so I think part of our jobs as academics and as part of this big group thinking a lot about data is to try to think about how are ways that we can clarify this and come up with ways that cut across the contingentness of all these phenomena. And that's something that we're sort of working towards, and we're hoping that there is some sort of kernel of truth that we can say where it's like it's okay or it's not okay in these precise conditions.
Okay, we have time for a question from the audience. If you have a question, please raise your hand, and we have someone who will bring a mic to you.
Thanks for the opportunity. So I'm from FinTech. So how do we generate the transaction data like PII or sensitive data for the synthetic data? Because we cannot get the signals or we cannot get the patterns without using the real data. And we have I'm from MasterCard, we have petabytes of data. So we are struggling with the synthetic data. Again, the models doesn't perform with the synthetic data, and just want to check with you.
So I guess maybe this is related to the synthetic data for the population health science project that Dan mentioned, right? So the technique that we use there, which I think could actually be quite generalizable and applied in financial domains as well, is to basically we start with the real data in a sort of a safe environment, sort of HIPAA compliant environment, so we could actually train models on that data. In that case, then we actually have differentially private language models actually trained on the real data, but with a very strong statistical guarantee. And then we use that differentially private language model to generate synthetic data. And then we have additional verifications on top of that to make sure that those are actually safe to be released for researchers to use. And I think that sort of speaks to this broader point that Dan nicely mentioned of getting access to these sensitive data is often a big barrier, maybe the big barrier to collaboration and research, right? And by having this platform that we built for releasing these synthetic but safe data, then that can sort of greatly reduce the barrier to starting these collaborations.
Great, thank you so much. Let's give them another round of applause.